Hello everyone, welcome to the lecture again. In the last lecture, we discussed about the equation of motion of a rigid body which is moving in a plane. We saw that the equation of motion can be analyzed by considering the pure translation of a point on the rigid body and the fixed axis rotation about that point. Today, we are going to discuss the work energy equation, and for that we need some of the basic concepts that we already know. Let me mention them here. So, we know that the work done by a force is u equal to integral f dot dr, where dr is the infinitesimal displacement and f is the force. Okay. We also know that the work done by a couple is u equal to integral m d theta. So, the situation is, suppose I have a rigid body and on this rigid body the couple is acting. So, we have two equal opposite forces F and minus F, that will give you the couple, and because of that this rigid body is, let us say, rotating, and it makes, let us say, rotate by an angle d theta, then u will be integral m d theta. Now, we also know that the kinetic energy of a rigid body, let us say, under pure translation is equal to T equal to half m v square. So, we have a rigid body and this rigid body is just translating, okay, with velocity v. Now, if the body is making a fixed axis rotation, okay. So, we have this rigid body and let us say this rigid body is rotating about point O with a velocity or the angular velocity omega, then the kinetic energy of the ith particle will be Ti equal to half mi ri omega square, okay, wherein this distance is ri, mass is mi, and its velocity v I will be ri into omega. Now, this omega is constant on the body because the whole body is rotating with a fixed angular velocity. Therefore, total T will be half omega, I can take outside the summation mi ri square, okay, and summation mi ri square is the moment of inertia of this body about point O. So, T will be half I naught omega square. Okay. Now, let us discuss the kinetic energy of a general plane motion. So, as we already discussed that the general plane motion can be analyzed by considering a point on the rigid body and then translation of that point plus the fixed axis rotation about that point. Let us say we choose point G, which is the center of mass of the rigid body. So, we have this rigid body, let us say its center of mass is moving with a velocity v bar, and the body is rotating about this G with an angular velocity omega. Then the kinetic energy T will be half m v bar square plus half I bar omega square. Okay. Here I bar is the moment of inertia of this rigid body about g. So, I is the moment of inertia of the rigid body about g or the mass center, and v bar is the translational velocity of the mass center. Okay. Mass center or g, and omega is the rotational velocity about the mass center. Okay. Now, let me show you that the kinetic energy of the rigid body will indeed be half m v square plus half I omega square. For that, let us consider a ith particle on the rigid body. Let us say its mass is mi, and as I said, this rigid body is moving with a translational velocity of v bar. Let us say it's the position of the mass mi is rho I, okay, then the mass mi will have a translational velocity of v bar plus a rotational velocity about g. Okay. So, it will be r omega. So, r is rho I into omega, okay, and that will be perpendicular to the line that joins mi to g. Okay. Now, from the geometry you can see that if this angle is theta, okay, then if I draw the perpendicular to v bar, then that angle will also be theta. Let us say the velocity of mass mi is vi, then this vi will be the sum of the translation velocity plus the rotational velocity. So, that will be v bar plus rho I into omega. Okay. Now, the kinetic energy T will be sum of half m I v I square. Let us put the value of v I from here. So, we will have half summation m I, and v I is v bar plus rho I omega square, okay, and we can expand this bracket term. So, it will be half summation m I v bar square plus half summation m I rho I square omega square plus summation m I v bar rho I omega cos theta, where theta is the angle between v bar and rho I omega. Let me call this equation number 1 and let us look at it term by term. Okay. So, the first term is summation half m I v bar square, and v bar is the translation velocity of the rigid body and also of all the particle. Okay. So, therefore, v bar is independent of the summation, we can take it outside. So, I have half v bar square summation m I, and summation m I is just m. So, we have half m v bar square. Now, let us look at the second term. The second term is summation m I. So, you have half also rho I square into omega square. Again omega is constant, so I can take it outside, half omega square summation m I rho I square, and summation m I rho I square is the moment of inertia about g. Okay. So, let me call it half omega square I bar. Okay. Now, let us look at the last term, that is summation m I v bar rho I omega cos theta. So, this I can write down as v bar because that is constant, omega is also constant. I have summation m I rho I cos theta. and rho I cos theta is the projection of rho I along the y direction. So, let me call it yi. Okay. Now, this yi is measured from G, which is the mass center, and because of the definition of the mass center, summation mi xi or summation mi yi will be 0. Okay. Why? Because G is the mass center. Okay. So, if we put this in 1, then we have T equal to half m v bar square plus half I omega square. Okay. Now, let me write down the work energy equation for the rigid body which is moving in a plane. Okay. So, we already know the work energy equation for the particle, and let us follow the same convention that we have followed earlier. So, we had T1 plus V1 plus U12 equal to T2 plus V2. Okay. Here T1 is the initial kinetic energy, V1 is the potential energy, wherein we consider the gravitational potential energy and the elastic potential energy. So, this has gravitational plus elastic potential energy, and U12 is the work done by external forces. Okay. Of course, other than the gravitational and elastic forces. Okay. And you have to note that the term T1 and of course T2, it will include the translational plus rotational kinetic energy. Okay. So, based on this, now let us look at a couple of problems. The first problem is the racing spheres. So, let me write down the statement. We have two objects, okay, a solid sphere and a solid cylinder. Both with the same mass m and radius r. If we release them, from rest at the top of an inclined plane, which object will win the race? Okay. And assume that the object roll down the ramp without slipping. Okay. So, we have the following situation, we have this ramp. Okay. To formulate the problem, let us say this height is h and this angle is theta. So, we have our object here. Okay. Now, to analyze this problem, we can use the work energy equation. Okay, the whole thing is moving in a plane, which is T1 plus V1 plus U12 equal to T2 plus V2. So, initially the object is at rest, therefore, T1 will be 0, the initial kinetic energy will be 0. V1 is the potential energy, so it has only the gravitational potential energy, that is equal to mgh. Now, the final kinetic energy T2 will be half m v square plus, so this is the translational kinetic energy, plus the rotational kinetic energy will be half I omega square. Okay. And finally, V2 will be 0, U12 is of course 0. So, let us put this in equation number 1. So, we have mgh equal to half m v square plus half I omega square, and omega we can write down in terms of v, because omega equal to v over r. So, therefore, I have 2 mgh equal to mv square plus I omega is v square divided by r square, and let me multiply by m and divide by m. So, that m will get cancelled, and we have 2 gh equal to v square 1 plus I over m r square, or v equal to square root 2 gh over 1 plus I over m r square. Okay. So, this is the velocity of the object when it covers a vertical distance of h. Now, let us find out the acceleration of the object. For that, we can use v square equal to u square plus 2 a s, and from the geometry s is equal to h over sin theta. So, let me call this as s. So, initial velocity u was 0. Let us put v square from here. So, we have 2 g h over 1 plus I over m r square equal to 2 a h over sin theta. Now, 2 and h will get cancelled. So, we have a equal to g sin theta over 1 plus I over m, and the radius of the object is given as r. So, let me write down r square. This is the acceleration of the object. Now, this tells you that the object with the smallest I over m r square will win the race. So, the object with smallest I over m r square will win the race. Now, let us look at another problem statement. A 30-pound slender rod AB is 5 feet long and is pivoted about a point O which is 1 foot from end B. The other end is pressed against a spring of constant K equal to 1800 pound per inch until the spring is compressed 1 inch. The rod is then in a horizontal position okay. Now, if the rod is released, from this position, determine its angular velocity as the rod passes through a vertical position. So, initially the rod is like this, okay. Its weight is 30 pound, which is going to act at the center of the mass. So, this is 1 feet and the whole length is 5 feet. So, therefore, this will be 2.5 feet. Okay. And so, this was the initial situation, and when the rod is released, then it goes into the vertical position, and we have to find out its angular velocity in that case. Okay. So, let us use the work energy equation. So, we have T1 plus V1 plus U12 equal to T2 plus V2. Okay. Initially the rod was at rest. So, T1 is equal to 0. Now, let us look at V1. Okay. Let me fix our reference point over here. So, there is no gravitational potential energy, we only have the spring energy. So, that will be half k x1 square. Okay. So, that will be half k is given, it is 1800 pound per inch. So, 1800 into 1 square, and that comes out to be 900 pound inch. Okay. Since all other parameters are given in feet, so let us write down this in feet also. We know that 1 feet equal to 12 inch. So, therefore, this will be 75 pound feet. Okay. Now, U12, there is no work done by external forces. So, that will be 0. Now, let us look at T2, the kinetic energy. So, it will be half m v bar square plus half I omega square. Now, let us find out half m v square. So, that will be half mass is weight divided by the gravitational constant, and the weight is 30 pound divided by g. G is 32.2 feet per second square. So, this is my mass into V, V is equal to R omega. Now, let us look at R. So, note that this length is 1, this is 2.5, therefore, from here to here it will be 1.5 feet. Okay. So, that is our R. So, R is 1.5 into omega square, okay, plus half I, moment of inertia of the rod about the center of mass will be ml square divided by 12, where L is the length of the rod. So, that will be, let me just write down ml square divided by 12. So, we have 1 by 12, mass is again 30 divided by 32.2 into L square. Now, the length of the rod is 5 feet. So, that will be 5 square. So, this is my moment of inertia into omega square. Now, this can be simplified and it comes out to be 2.019 omega square. Now, let us look at V2. V2 is the potential energy in that situation. So, that will be there is no spring force now. So, it is only the gravitational potential energy. So, that will be mg into h. So, mg is 30 and h is 1.5. So, that is 45 feet to lb or the pound. Okay. So, let us put this in equation number 1. So, we have 0 plus 75 plus 0 equal to 2.019 omega square plus 45, and that gives you omega equal to 3.86 radian per second. Okay. Now, let us look at one more problem. Problem statement is the wheel rolls up the inclined on its hubs without slipping and is pulled by the 100 Newton force applied to the cord wrapped around its outer rim. If the wheel start from rest, computes its angular velocity omega, after its center has moved a distance of 3 meter up the incline. The wheel has a mass of 40 kg with center of mass at O and has a centroidal radius of gyration of 150 mm. So, in this question we have a wheel which has a hub, and this wheel moves up on the inclined plane which makes an angle of 15 degree from the horizontal. So, we have this hub, and then this hub is connected to a wheel. The radius of the hub is 100 millimeter and the radius of the wheel is 200 mm. Now, it is given that the center move a distance of 3 meter up the incline. So, when the center move a distance of 3 meter, in that case let us see how much the outer rim will move, and that we can find out using very simple geometry, because this distance is 100 mm. So, we have 100 mm, and in that case the center moves a distance of 3 meter, okay, and the outer rim is at a distance of 300 mm. Okay. So, now let us say it is 300 mm. In that case, how much the outer rim will move? So, how much is this? Okay. And you can find out from the very simple geometry that if this is 100, then this one is 3 meter. So, therefore, when this is 300 mm, then that will be 9 meter. Now, to find out the angular velocity, let us use the work energy theorem. So, we have T1 plus V1 plus U12 equal to T2 plus V2. Let us call it equation number 1. Now, initially the whole thing was at rest. So, therefore, T1 was 0, and let us put our reference point at the bottom. Okay. So, therefore, initial potential energy was also 0. Let us look at the work done on the wheel. So, U12 will be the distance multiplied by the force. So, the distance was 9 meter, okay, into the force. Note that the force was applied here, therefore, we have calculated how much distance this point has travelled. So, that was 9 meter multiplied by 100 Newton. So, that is 900 Newton meter. Now, let us look at the final kinetic energy. So, that will be half mv square plus half I omega square. Now, let us write down half mv square. So, that will be half, m is given, it is 40 kg, and v is equal to r omega, r is 0.1 into omega square, plus we have half I omega square, and I is equal to m k square, where this k is the radius of gyration, and it is given that radius of gyration is 150 mm. So, therefore, that will be m is 40 into k square, k is 0.15 square into omega square. Okay. Now, let us look at V2. V2 will be the potential energy. So, that will be mgh. So, m is 40, g is 9.81 into h. So, it travel a distance of 3 meter on 15 degree inclined. So, therefore, h will be 3 sin 15 degree, okay, because this is 3. So, therefore, that distance will be 3 sin 15. Okay. Let us put all this in equation 1. So, we have T1 equal to 0 plus V1 equal to 0 plus U12 equal to 900, that is equal to T2 plus V2. So, T2 comes out to be 0.65 omega square plus V2 comes out to be 305. So, this is equal to 0.65 omega square, and that is equal to 305. So, from here we get omega equal to 30.3 radian per second. With this, let me stop here. See you in the next class. Thank you.